All right, let's dive into a discovery that is, and I'm not exaggerating here, something straight out of science fiction. Scientists have just found a state of matter in a single sheet of carbon atoms that appears to break a fundamental century-old law of physics. So how on earth did they do it? Let's get into it.
Now, this isn't happening in some far-off galaxy or a giant particle collider. We're talking about graphene, a material that's just a single atom thick. What researchers found is that electrons inside it weren't acting like individual particles anymore. Instead, they were flowing all together like a bizarre, perfect liquid.
So to really get why this is such a huge deal, we've got to first talk about the rule that was just broken. And I mean, completely shattered.
For more than 100 years, the Wiedemann-Franz law has been like gravity for materials physics. It's a simple idea. In any metal, how well it conducts electricity is directly linked to how well it conducts heat. If one is good, the other has to be good too. They're tied at the hip. And this held true for every single metal we've ever tested. Well, until now.
When the researchers measured how heat was moving in their special graphene sample, it wasn't just a little bit off. It was nearly 300 times greater than what the law said was possible. Think about that. It's less like two friends walking out of sync and more like one of them teleported across town while the other is still tying their shoes. This was a massive, undeniable violation of the law.
So how is that even possible? I mean, a law that stood for a century just got broken. To understand it, we have to rethink something really basic, how electrons actually move through stuff.
You know, in a normal metal, you can picture electrons like billiard balls on a messy table. They zip around, but they're constantly crashing into impurities and vibrating atoms, scattering in all directions. We call that diffusive flow. But in this graphene, something totally different was happening. The electrons started colliding with each other so much that they stopped scattering randomly. Instead, they began moving as one, in a collective, coordinated way, kind of like water flowing smoothly down a river. That's hydrodynamic flow.
And here's the kicker. This isn't how all graphene behaves, not even close. This weird, fluid-like state only shows up when the graphene is exceptionally pure. I mean, ultra clean. It's a really fragile and exotic quantum state that physicists have been hunting for a long time, a state where the normal rules of the road for electrons just fall apart.
So let's properly meet the material at the center of this whole story, graphene, and the truly strange state of matter it can create.
So you've probably heard of graphene, right? The wonder material. It's this super strong, superconductive sheet of carbon atoms in a honeycomb pattern. But its secret weapon for our story is something called the Dirac point. Think of it as a state of perfect balance. There's no net electrical charge because you have a perfect sea of electrons and their opposites, these things called holes. And this perfect balance is the stage where all the quantum drama is about to unfold.
And that brings us to the holy grail here, the Dirac fluid. For years, the theory was that if you could make graphene pure enough and tune it perfectly to that Dirac point, the electrons and holes would stop being individual particles and start flowing together like a single exotic liquid with almost zero friction. Finding it was the grand prize.
Okay, so the theory is out there, but how did a team of physicists finally go out and prove that this Dirac fluid is actually real? Let's walk through the experiment.
The #1 challenge was getting the graphene clean enough. See, any tiny imperfection would disrupt the flow and hide the fluid behavior. The solution was basically to make an atomic scale sandwich. They tucked the graphene sheet between two ultra-flat layers of another material called hexagonal boron nitride. This protected it, creating the pristine playground the electrons needed to finally start moving like a liquid.
Now, the experiment itself was just brilliant. They found a way to gently warm up only the electrons without heating up the material itself. Then, using this super sensitive technique to measure the electron's temperature, they could track exactly how both charge and heat were flowing at the very same time. And that was the key to put any old law to the test.
And the results? Whoa! Just look at this. The bar on the left is the amount of heat flow that the century-old law predicted. The bar on the right? That's what they actually measured. This chart is the smoking gun. It's definitive proof that charge and heat had become completely decoupled. The law was officially broken.
But this story gets even better. This wasn't just some random giant violation. Hiding in their data, the researchers found something even more profound, a universal constant of nature.
So the theory didn't just predict a fluid, it predicted that if this fluid was real, its electrical conductivity would hit a very specific universal value. It wouldn't matter how big the graphene sample was or what shape it would always be the same number. Think of it like a unique fingerprint for this exact state of matter, a fingerprint determined only by the fundamental constants of nature itself.
And this is the predicted fingerprint right here. Look what it's made of. E, the fundamental charge of an electron, and H, Planck's constant. These aren't just random variables. These are two of the most basic numbers woven into the very fabric of our quantum universe.
And here it is, the eureka moment. The team took all the data from all their different devices, and when they crunched the numbers, the results all landed on that one single universal value that theory had predicted. It was a perfect match. This was the moment they knew for sure they hadn't just broken a rule. They had discovered a brand new fundamental state of quantum matter. So why does all this matter beyond just rewriting an old physics textbook? Well, because this tiny atom-thick sheet of graphene has just become a laboratory for studying some of the most extreme and exotic physics in the entire universe.
And this is where things get truly mind-bending. The perfect fluid of electrons they found in this little chip, it behaves almost exactly like another perfect fluid, the quark-gluon plasma. That's the state of matter that's thought to have filled the entire universe just microseconds after the Big Bang. We can now study the physics of the primordial universe on a lab bench at room temperature.
And the connections get even weirder. This fluid flows with almost zero friction, approaching a fundamental lower limit. And where does the prediction for that limit come from? Not material science, but from the physics of black holes. We are literally connecting the behavior of electrons on a chip to the properties of an event horizon. It's absolutely wild.
By creating this tiny, perfect quantum laboratory, we've found a system that bridges the gap from tabletop physics all the way to the cosmos. And it leaves us with this incredible question to think about. What other secrets of the universe are just waiting to be discovered, hiding inside a single layer of atoms?